What if everything you thought you knew about time was just the tip of the iceberg? Picture a universe where time isn't a straight line stretching from past to future, but a tangled web of dimensions, each one bending, twisting, and folding in ways that defy our everyday experience. We've all felt time slipping through our fingers the way an hour can drag or vanish in a blink. But what if those moments aren't just fleeting? What if they're glimpses of something far stranger lurking beneath the surface of reality? For centuries, scientists and philosophers have wrestled with the nature of time, treating it as a relentless, one-way river. But cutting-edge theories are now revealing a cosmos where time might have hidden layers, like pages in a book we've only just begun to read. Imagine dimensions where time loops back on itself, where parallel moments exist side by side, or where the future might even influence the past. These aren't just sci-fi fantasies, they're real possibilities emerging from the frontiers of physics, challenging everything we assume about cause and effect, existence, and even the meaning of now. In this journey, we'll uncover 30 of the most astonishing theories about time's hidden dimensions, ideas that will stretch your mind to its limits. From the mind-bending implications of string theory to the eerie predictions of quantum mechanics, each one peels back another layer of the cosmic mystery. Some will sound like pure magic, others like nightmares, but all of them are backed by the sharpest scientific minds of our age. So buckle up. By the time we're done, you might never look at a clock or the universe the same way again. The first theory shatters our everyday notion of time as something flowing instead. It suggests the entire universe is frozen in place. Picture reality as an immense, unchanging sculpture where every moment from the Big Bang to the heat death of the cosmos exists simultaneously. This is called eternalism, and it treats time like just another dimension of space. Think of a loaf of bread where each slice is a single moment stacked together eternally. You wouldn't say one slice is more real than another, they all just are. Einstein's theory of relativity supports this mind-bending idea. His equations show that time isn't absolute, it stretches and warps depending on gravity and motion. What you experience as now could be someone else's past or future, depending on how fast you're moving. But here's where it gets stranger. If the future already exists, does free will disappear? Philosophers have wrestled with this for centuries. Some argue that choices still matter because your future self is simply part of the block, living out decisions you haven't made yet from your perspective. Others claim this makes life feel like a cosmic film reel, predetermined and unchangeable. Imagine standing outside the block universe, watching your birth, your first heartbreak, and your last breath all at once, not as memories or prophecies, but as fixed points in a grand, unmoving structure. It's a humbling thought, forcing us to ask, is time's flow just an illusion, a trick of our limited perception? And what about déjà vu? Could those eerie moments of recognition be glitches where our brains momentarily perceive time as it truly is a single, unchanging landscape? Science fiction loves this idea, but physicists take it seriously too. Experiments with quantum particles show effects appearing before their causes, as if time's arrow isn't always straight. If eternalism is correct, death might not be an ending, just another slice in the loaf, forever preserved in the universe's vast tapestry. So next time you glance at a clock, consider this. Every tick is less a countdown and more a tour guide, pointing you to the next exhibit in an already completed museum of reality. The second theory confronts a puzzle we all take for granted. Why does time only move forward? Drop an egg on the floor and it shatters into pieces. But no matter how long you wait, those fragments will never spontaneously reassemble into a whole egg. This relentless one-way street is known as the arrow of time, and it's deeply tied to a concept called entropy, the universe's tendency toward disorder. In the late 1800s, physicist Ludwig Boltzmann made a startling realization. The flow of time might just be a side effect of statistics. Imagine a deck of cards fresh from the box, perfectly ordered by suit and number. Shuffle it once and it's slightly disorganized. Keep shuffling and the cards descend into chaos. The universe works the same way. Particles start in neat, low entropy states like the tightly packed energy of the Big Bang, but over eons they spread out, creating the mess we call reality. Here's the twist. Boltzmann suggested that if you waited long enough, random particle movements could briefly recreate order, like a shuffled deck accidentally returning to its original sequence. Does that mean time could reverse? Some theories say yes, but only for a universe willing to wait longer than eternity. Then there's the chilling endgame, heat death. If entropy keeps increasing, eventually every star burns out, every black hole evaporates, and the cosmos becomes a lukewarm soup of scattered particles, incapable of any meaningful change. In this frozen future, the very concept of time loses its meaning. No events, no causes, just endless stillness. But why doesn't time run backward now? Some theorists propose an eerie answer. We're simply on the downhill slope of entropy's mountain. The Big Bang set the universe on this path, making forward the only direction we remember. Others speculate that multiple arrows of time could exist in parallel universes, with some civilizations experiencing reality in reverse. Picture watching a film where smoke pours into a cigarette, flames cool objects, and people rise from their graves. That might be everyday life in a mirrored cosmos. The arrow of time isn't just physics, it's the reason we have memories instead of premonitions, why we age instead of grow younger. But if entropy is the engine driving time forward, what does that say about free will? Are we just spectators riding the universe's slide into chaos, or does consciousness somehow bend the rules? One thing's certain, every time you watch milk swirl into coffee, you're glimpsing the deep, irreversible law that stitches the fabric of reality. Now let's peel back another layer of time's mystery. What if it's not just a line or a block, but a fabric woven from dimensions we can't even perceive? This is where the boundaries of physics stretch into the surreal. Imagine time as a vast, rippling sheet like the surface of a pond, except this pond has currents flowing in directions we can't see, hidden dimensions folded into the very structure of reality. This idea traces back to the early 20th century when two physicists, Kaluza and Klein, proposed a radical theory. They suggested that our universe might have more than just the three spatial dimensions we know: height, width, and depth. Hidden within the fabric of existence could be tiny, curled-up dimensions, so small they're invisible to our senses, yet profoundly shaping how time and gravity behave. Picture a garden hose. From far away, it looks like a simple line, but up close, you realize it's actually a tube, a one-dimensional line wrapped around a second circular dimension. Time might operate the same way, existing in unseen folds that influence everything from the motion of planets to the passage of seconds. String theory takes this even further, proposing that reality is built from tiny vibrating strings, and these strings require 10 dimensions to function. In this framework, time isn't just a singular flow. It's a dynamic interplay of higher dimensional threads, each vibrating at different frequencies. Some theorists even speculate that these hidden dimensions could host alternate timelines, parallel universes where time moves in ways we can't begin to fathom. Picture a symphony where each instrument plays a different melody in a different dimension, yet together, they create the unified experience we call now. But how would higher dimensions explain déjà vu, or those eerie moments when time seems to stutter? One possibility is that our brains occasionally stumble into these hidden layers, like a radio picking up a faint signal from another station. If time is a fabric, could consciousness itself be threading through its folds, sometimes brushing against moments that should be out of reach? And what about black holes? These cosmic anomalies might be portals where the fabric of time frays, exposing the seams between dimensions. Near a black hole's event horizon, time slows to a crawl, an effect predicted by Einstein's relativity. But in higher dimensional models, black holes could be knotting time into loops or tearing it entirely, creating pathways to other epochs or even other universes. The implications are dizzying. If time is a higher dimensional structure, it could mean that every moment we experience is just a shadow cast by something far grander, a reality where past, present, and future merge into a single, intricate design. Next time you check your watch, ask yourself, are you really counting seconds or just tracing the faint echoes of a cosmic tapestry we're only beginning to unravel? What if the universe had secret shortcuts where time folded back on itself like a twisted ribbon? Enter closed timelike curves, the mind-bending loopholes in Einstein's equations where the future could circle back to touch the past. These hypothetical pathways, known as CTCs, aren't just sci-fi fodder. They emerge straight from the cold, hard math of general relativity, suggesting that under extreme conditions, space-time could curve so severely that time becomes a loop. Picture a hiker walking in a straight line across a mountain, only to end up back where they started, except here, the mountain is reality itself, and the hiker is you, arriving at a moment you've already lived. The first clue came from an unlikely source, Kurt Gödel, the mathematician who shattered our understanding of logic. In 1949, he handed Einstein a birthday present that unsettled him: a solution to relativity's equations describing a rotating universe. In Gödel's cosmos, everything spins, dragging spacetime along with it like a cosmic whirlpool. If you traveled far enough in such a universe, you'd eventually return to your own past, like a record needle circling back to an earlier groove. Einstein was troubled. The equations allowed it, but the implications defied intuition. Cause and effect could unravel, with events triggering themselves in endless, paradoxical loops. So how would a closed time-like curve actually work? Imagine a wormhole, a tunnel through spacetime where one end moves at near light speed while the other stays still. Time slows down for the speeding end due to relativity, creating a bridge between different moments. Step in, and you might exit before you even left. Theoretical physicist Kip Thorne toyed with this idea in the 1980s, showing how such a structure could exist without violating known physics, though it would require exotic matter with negative energy to hold the tunnel open. But here's the catch: CTCs don't just bend time, they twist logic into knots. The infamous grandfather paradox rears its head. What if you traveled back and prevented your own birth? Some physicists argue the universe would forbid such contradictions, adjusting events like a self-correcting script. Others propose the Novikov self-consistency principle, where any time traveler's actions were always part of history, making free will an illusion. Picture trying to change a movie you're already in. Every new choice was always there, hidden in the film's frames. Yet the most startling idea comes from quantum mechanics. In 2009, physicist Seth Lloyd suggested CTCs might exist microscopically, woven into the fabric of reality at the quantum level. Particles could loop through time, interacting with their past selves in ways that look like bizarre quantum effects to us. This could explain phenomena like entanglement, where particles instantly influence each other across vast distances, as if they're secretly sharing information through hidden time highways. Are closed time-like curves just mathematical quirks, or could they be real? Black holes might hold clues. Near a spinning black hole's ergosphere, space-time twists so violently that some theorize natural CTCs could form. If you survived the trip, you might emerge in another era, though the universe might conspire to keep history consistent, leaving you a spectator, not an author of the past. One thing's certain: if CTCs exist, time isn't a river but a Möbius strip, where beginnings and endings are just illusions of perspective. What if time isn't something we move through, but something projected onto us like light flickering across a movie screen? This is the core of the holographic principle, a theory so strange it redefines reality itself. Imagine the universe as a cosmic illusion where every event, every moment you've ever experienced is just a shadow cast by information encoded on a distant two-dimensional surface. Your memories, the ticking of clocks, even the sensation of time passing, none of it would be fundamental. Instead, it's all a grand performance, a hologram unfolding from a hidden layer of reality we can't see. The idea traces back to Leonard Susskind, the physicist who helped pioneer string theory. In the 1990s, he and Nobel laureate Gerard T. Hooft made a startling observation. The information inside a black hole isn't lost when matter vanishes beyond its event horizon. Instead, it's smeared across the surface like a tattoo on the edge of oblivion. This led to a radical thought: what if everything works this way? If a black hole's interior can be described entirely by data on its boundary, could the entire universe be similarly encoded? Susskind's calculations suggested yes, our three-dimensional reality, complete with time's relentless march, might just be a projection from a flat, two-dimensional substrate at the edge of the cosmos. Think of it like a credit card hologram. Tilt it, and a three-dimensional image seems to float above the surface, but in reality, every detail is stored on the flat, shiny strip. The universe could operate the same way. Time's flow, just part of the illusion. That eerie sense of déjà vu may be a glitch in the projection. Even consciousness itself might be a side effect of information processing on a boundary we'll never perceive. The implications unravel everything. If time is holographic, free will could be a script written in advance on this distant surface. The Big Bang might not have been an explosion in space, but a rendering like a projector flicking on. And entropy, just the universe's way of unpacking compressed data into the vibrant, chaotic world we experience. Here's the wildest twist: the holographic principle could solve one of physics' biggest headaches, the conflict between quantum mechanics and gravity. Quantum laws govern the tiny, relativity handles the cosmic, but holography suggests they're two sides of the same coin. Gravity in our 3D world might emerge from quantum interactions on the 2D boundary, like the plot of a novel unfolding from inked letters on a page. Could we ever prove this? Some physicists are trying. Experiments with superconductors have revealed phenomena where electrons behave as if they're in a lower dimensional system. And strange correlations in the cosmic microwave background, the afterglow of the Big Bang, hint at patterns that might align with holographic encoding. If Susskind is right, time isn't a river or a dimension, it's a rendering, a flickering projection from the edges of existence. So the next time you check your watch, ask, are you measuring seconds or just reading pixels on the universe's deepest screen? What if time itself could crystallize, forming structures that pulse with the regularity of a heartbeat, except these beats never slow, never fade, and require no energy to keep ticking? This isn't science fiction. It's the bizarre world of time crystals, a discovery so radical it redefines what time even means. In 2012, Nobel Prize-winning physicist Frank Wilczek dared to ask, could there be phases of matter, like solids or liquids, but for time instead of space? The answer shook the foundations of physics. Wilczek imagined a system where atoms don't just arrange themselves in repeating spatial patterns, like the lattice of a diamond, but in repeating temporal patterns. Picture a cosmic metronome that clicks back and forth forever, not because it's powered by some hidden battery, but because that's simply its natural state. This defies everything we know. The second law of thermodynamics says all systems must eventually run down, succumbing to entropy. Yet time crystals sidestep this rule, oscillating perpetually in what Wilczek called a new form of quantum dance. The real shock came when labs actually built them. In 2017, two teams, one at Harvard, another at the University of Maryland, created time crystals using chains of ytterbium atoms and diamond defects chilled to near absolute zero. When nudged with a laser pulse, these systems didn't respond like ordinary matter. Instead, they pulsed at a rhythm slower than the laser's frequency, as if time itself had a hiccup. Even stranger, this rhythm persisted indefinitely, resisting the universal pull toward equilibrium. It's like pushing a child on a swing and watching them sway at their own stubborn pace, no matter how hard or soft you push. How is this possible? The secret lies in quantum entanglement, where particles become so deeply linked that disturbing one instantly affects another, no matter the distance. In time crystals, entanglement locks atoms into a synchronized dance, allowing them to flip states in a cycle that repeats like clockwork without losing energy. It's not perpetual motion, it's perpetual structure, a shape carved into time itself. Wilczek's idea hints at something profound. Time might not be the blank canvas we assume. Just as space has mountains and valleys, time could have its own topography, ridges and troughs where matter naturally settles into rhythmic patterns. Some theorists even speculate that time crystals could be fragments of a deeper temporal order, like ice crystals forming on a window pane. If true, the universe might be filled with invisible clocks, ticking silently beneath the surface of reality. Practically, time crystals could revolutionize quantum computing. Their stability makes them ideal for error-resistant qubits, potentially unlocking computers that harness the flow of time itself. But the philosophical implications are even wilder. If matter can exhibit temporal order independent of energy, does that mean time is more fundamental than we thought? Could the universe host natural time crystals, humming away in the hearts of neutron stars or the aftermath of the Big Bang? One thing's certain, time crystals prove that even time, the most familiar force in our lives, still holds mysteries that defy intuition. They're not just a new state of matter. They're a glimpse into a universe where time isn't just a backdrop but an active, sculptural force. Next time you glance at a ticking clock, remember, somewhere, atoms are keeping time in a way no clock ever could, locked in a quantum waltz that never, ever ends. The Wheeler-DeWitt equation is the ultimate cosmic buzzkill, a mathematical sledgehammer that smashes time into oblivion at the deepest level of reality. Born from the minds of physicists John Wheeler and Bryce DeWitt in the 1960s, this formula was meant to unite quantum mechanics with Einstein's general relativity. Instead, it delivered a shocking twist. When you peer into the quantum bedrock of the universe, time vanishes entirely. No ticking clocks, no flowing moments, just eerie, frozen equations describing a reality where now has no meaning. To grasp how radical this is, picture a clock submerged in liquid nitrogen, frozen so completely that its hands can't move. The Wheeler-DeWitt equation does something similar to the entire cosmos. It describes a universe where quantum gravity reigns, and in that domain, time isn't just irrelevant, it's mathematically erased. The equation treats the universe as a static object, like a snapshot of all possible configurations of space and matter, with no built-in direction or flow. Think of a DVD containing every frame of a movie stacked together without play or pause buttons. The film's story exists, but the experience of watching it unfold. That's just an illusion created by our limited perspective. This timeless universe raises existential questions. If time isn't fundamental, why do we perceive it so vividly? Some theorists argue consciousness itself stitches together moments like a projector flickering through film frames. Others suggest time emerges from quantum entanglement, with particles interacting in ways that create the illusion of sequence. Imagine standing in a crowd where everyone claps in perfect rhythm. The sound seems continuous, even though it's made of discrete events. Time might work the same way, a collective effect of countless quantum processes. The Wheeler-DeWitt equation also ties into the infamous problem of time in physics. While Einstein showed time is relative, quantum mechanics treats it as a fixed backdrop. The equation bridges this gap by eliminating time altogether, forcing physicists to confront a reality where beginnings and endings are human constructs. Even black holes, those notorious time benders, become timeless objects in this framework, their event horizons mere features in a frozen quantum landscape. But here's the kicker: if time isn't real, what does that mean for free will? Are choices just predetermined configurations in a cosmic DVD, waiting to be played by our brains? Philosophers split on this. Some embrace temporal naturalism, suggesting time emerges like temperature does from atomic motion, real in practice but not fundamental. Others see it as proof we're living in a deeper, stranger reality than we ever imagined. The equation isn't just abstract math. Experiments with quantum gravity hints, like the behavior of space-time foam or holographic principles, might one day test its predictions. Until then, the Wheeler-DeWitt equation stands as a monument to physics' most humbling lesson. The universe owes us no intuitive truths. Time feels like the most solid part of our lives, but at the quantum level, it might be nothing more than a trick of the light. So the next time you glance at a clock, remember, those ticking seconds could be the universe's most convincing mirage. Imagine standing at a crossroads where every possible path you could take splits into a new reality, not just metaphorically but literally. This is the spine-tingling promise of the many worlds interpretation, where time doesn't just flow forward, it branches endlessly, spawning alternate universes with every quantum hiccup. Proposed by physicist Hugh Everett in 1957, this theory turns the entire cosmos into a fractal of possibilities, where every decision, every random event spawns a new timeline. Forget parallel worlds where you might have different hair or career choices. This is far wilder. In Everett's vision, all quantum outcomes happen somewhere. Schrödinger's cat isn't just alive or dead. It's both in separate, equally real universes unfolding side by side. The math behind this is deceptively simple. Quantum mechanics describes particles as probability waves, ghostly clouds of maybes that collapse into definite states when observed. But Everett asked, what if no collapse happens? What if every possible outcome persists, with reality itself dividing like a hall of mirrors to accommodate each one? Picture a river forking into countless streams, each carrying a version of you living out every conceivable variation of existence. The version reading this script right now is just one thread in an infinite tapestry of timelines. Here's where it gets dizzying. These branches aren't sci-fi what-ifs, they're baked into the universe's operating system. When an electron zigzags instead of zagging, reality doesn't choose, it forks. Your morning coffee could have gone left or right when you knocked it over, and in some universe it did. This means time isn't a single arrow but a tree, with roots in the Big Bang and branches stretching toward every possible future. Somewhere, dinosaurs still rule Earth. Somewhere, you never hit snooze today. Somewhere, the laws of physics themselves might differ. Critics argue this is absurdly wasteful. Why would nature spawn infinite universes just to avoid quantum collapses? But supporters counter, waste by whose standards? The multiverse doesn't need extra energy to branch. It's simply how quantum probability propagates. And the math works. Unlike other interpretations requiring mysterious observers or hidden variables, many worlds treats quantum mechanics as is no extra ingredients. But how does this connect to time's hidden dimensions? If every quantum event spawns new universes, time isn't linear. It's a sprawling network where now is just the local node you happen to inhabit. Some theorists suggest these branches might not be entirely separate. Tiny quantum fluctuations could allow faint leaks between timelines, like echoes from roads not taken. Ever had a dream so vivid it felt like a memory from another life? Or a gut feeling that defied logic? In a branching multiverse, those might be more than misfires. They could be whispers from alternate versions of you, vibrating through the quantum foam. And here's the kicker: if time branches endlessly, then every possible outcome must exist somewhere. Every tragedy averted, every heartbreak undone, every lottery won, just not by this version of you. It's either the most comforting thought in existence or the most isolating, depending how you look at it. The many worlds interpretation doesn't just redefine time, it turns the cosmos into a choose-your-own-adventure book where every page is being read simultaneously. So next time you hesitate between two choices, remember, in some universe you didn't, and that version is just as real as the one reading these words right now. What if the universe had no beginning and no end, just an endless cycle of rebirth, where time itself resets like a phoenix rising from its own ashes? This is the heart-stopping vision of Sir Roger Penrose's conformal cyclic cosmology, a theory so audacious it rewrites cosmic history as an infinite loop of creation and destruction. Picture a cosmos where every black hole's death cry becomes the Big Bang of a new eon, where the far future of one universe seamlessly stitches itself to the dawn of the next. Time doesn't just flow here, it folds back on itself in a cosmic Ouroboros, swallowing its own tail to begin anew. Penrose's idea shatters the standard narrative of a one-and-done Big Bang. Instead, he proposes that our universe is just one page in an endless book, each chapter separated by an eerie phase called conformal rescaling. As a universe expands toward heat death, its particles spread thin, its energy diluted to near nothingness. The very concept of time and distance loses meaning. At this critical point, the universe's vast emptiness can be mathematically rescaled to resemble a hot, dense singularity, miraculously aligning with the conditions of a new Big Bang. It's like zooming out on a fractal until its edges blur, then zooming back in to find a fresh, intricate pattern. But how could information survive this cosmic reset? Penrose points to black holes specifically, their Hawking radiation. As black holes evaporate over eons, they imprint the universe's information onto spacetime itself, like shadows burned into the fabric of reality. These imprints, called Hawking points, might carry faint echoes of past eons into new ones. Imagine finding a message in a bottle washed ashore. Its ink faded but still legible, except the bottle is a remnant of a vanished universe, and the message is written in the language of gravitational waves. The real shocker, we might already have evidence. Penrose and colleagues claim to have spotted concentric rings in the cosmic microwave background, the afterglow of the Big Bang. That could be gravitational wave fingerprints from collisions of supermassive black holes in the previous eon. If confirmed, these rings would be the ultimate cold case, forensic traces of a cosmos that existed before time as we know it began. Critics argue that cyclic cosmology violates the second law of thermodynamics. How can entropy reset if it always increases? Penrose counters that gravitational entropy works differently. Near the end of an eon, all matter decays into massless particles like photons, effectively resetting the disorder clock. Think of it like erasing a chalkboard. The scribbles entropy vanish, leaving a blank slate for new equations. The philosophical implications are staggering. If time is cyclical, does that mean every moment, every choice, every tragedy, every triumph will replay infinitely? Not quite. Each eon starts with similar initial conditions, but quantum fluctuations ensure no two cycles are identical. You might exist again in the next universe, but your life would unfold differently, like variations on a cosmic theme. Penrose's vision is either the most beautiful idea in cosmology or the most humbling. It suggests that time isn't a straight line or even a branching tree. It's a Möbius strip where endings and beginnings are illusions. The heat death of our universe wouldn't be a finale but a prelude. Every black hole's demise plants the seed for a new cosmic dawn. So when you look up at the night sky, consider this. Those stars aren't just remnants of our Big Bang. They might be recyclable material for universes yet unborn, in a cycle without start or finish, where time itself is forever young. Quantum entanglement, the spooky link that binds particles across vast distances, might hold the key to time's greatest secret, its very existence. Recent breakthroughs suggest entanglement doesn't just connect particles, it could weave the fabric of time itself, stitching moments into a coherent flow where there was only timeless void. This radical idea turns conventional physics on its head. Instead of time being a backdrop for quantum events, entanglement might be the loom that generates it, pulling order from chaos to create the illusion of before and after. The puzzle starts with a simple observation. In isolated quantum systems, time has no meaning. Particles exist in superpositions, clouds of potential with no definite states. But when entanglement kicks in, these particles sync up, their properties locked in step like dancers in a cosmic tango. Physicists like Sean Carroll and Eugenio Bianchi argue this synchronization isn't just correlation, it's the genesis of time's arrow. Imagine two people stranded on separate islands, each flipping coins randomly. Their results seem unconnected until one day they notice their coins always match, even though neither controls the other. That eerie alignment is entanglement. Now picture scaling this up to every particle in the universe, their interactions building a network of mutual influence so dense that it crystallizes into what we experience as time. Lab experiments are starting to catch up with the theory. In 2019, researchers at the University of Vienna entangled photons and watched how their states evolved. The shocking result: the more entangled the particles became, the more reliably they defined a sequence of events like tiny clocks emerging from quantum fog. It's as if entanglement doesn't just happen in time, it constructs time's scaffolding, one interaction at a time. But here's the twist: if time emerges from entanglement, then now might just be a local phenomenon. In regions with sparse entanglement, like the vacuum of deep space-time, could become slippery or even meaningless. Black holes where extreme gravity shreds quantum links might be places where time unravels. Meanwhile, dense networks of entangled particles like those in our brains could create pockets of vivid temporal flow. This could explain why time feels so tangible to us, yet remains abstract in equations. The implications ripple outward. If entanglement builds time, then quantum gravity, the holy grail of physics, might not need to quantize time at all. Instead, time would emerge naturally, like temperature arising from atomic motion. It also redefines causality. What if cause and effect aren't fundamental, but side effects of particles getting entangled in just the right way? Critics ask, how do we reconcile this with relativity, where time bends and warps? The answer might lie in scale. Einstein's time operates in the cosmic theater, while entanglement's time emerges backstage in the quantum green room. Bridging these realms could unlock secrets about the Big Bang, a moment when the universe's particles were maximally entangled, possibly igniting time's very first tick. So next time you check your watch, consider this. Those seconds might not be flowing, they're forming, forged in the invisible quantum bonds that bind every atom in your body to the universe's distant edges. Time isn't handed to us, it's built moment by moment by the silent conversations of particles deciding together what now even means. What if time isn't smooth and continuous like a river, but more like a flickering film strip, a sequence of tiny, indivisible moments strung together by cause and effect? This is the startling premise of causal set theory, a radical approach that rewrites spacetime as something granular like cosmic confetti. Forget the familiar fabric of relativity. Here, reality is built from discrete atoms of existence, where time emerges not from flowing but from the simple question, what causes what? The theory's roots trace back to physicist Raphael Sorkin in the 1980s, who asked a deceptively simple question: what if spacetime isn't fundamental? Just as water feels continuous but is actually made of molecules, the universe might be constructed from finite, irreducible pieces called causal sets. Imagine a vast cosmic ledger where each entry represents an event, a particle collision, a star's birth, your first breath, and the only rule is that some events must come before others. No smooth geometry, no warping fabric, just raw cause and effect relationships, like dots connected by arrows in a billion-year flowchart. Here's the twist: time isn't a dimension in this model. It's an illusion that arises when you zoom out, like the blur of a spinning wheel creating the illusion of motion. Two events might have no inherent time between them, just a causal link like dominoes frozen mid-fall. Only when you step back does the sequence appear to flow. It's a cosmic magic trick where the universe's deepest level is a silent, timeless network of before and after, with no clocks, no seconds, just cold, hard causality. Why does this matter? For one, it could solve black hole paradoxes. In Einstein's relativity, black holes crush spacetime into singularities, points of infinite density where physics breaks down. But in causal set theory, there's no infinity, just a finite chain of causal links coming to an end. Picture a book where the last page isn't torn off, it simply has no next page. The story stops not with a bang but with a period. The theory also redefines entropy. Normally, entropy grows as time moves forward, but in a causal set, it's the other way around. Time emerges because entropy increases. Think of a pile of sand. Each grain's position depends on where the grains before it landed, a causal chain creating the illusion of time's arrow. This flips the script on thermodynamics, suggesting entropy isn't driven by time, it creates time. Experiments are still catching up, but subtle clues hint causal sets might be real. Quantum gravity models predict spacetime should appear foamy at tiny scales, like static on a TV screen. Some interpretations of this spacetime foam align eerily with causal set predictions, a universe pixelated into fundamental units. And if the theory holds, it could mean our smooth, flowing experience of time is just a useful approximation, like mistaking a mosaic for a painting when you stand too far back. Philosophers love this idea because it turns free will into a cosmic game of dominoes. If reality is just causal links, are our choices predetermined? Not necessarily. Just as a single domino can tip in multiple directions depending on microscopic bumps, causal sets might allow for quantum randomness, where next isn't fixed until it happens. The most beautiful part, causal set theory doesn't abolish time, it demystifies it. Time isn't a force or a dimension, it's a side effect of the universe's relentless connectivity. Every time you recall a memory or anticipate a future moment, you're not surfing a temporal wave, you're tracing the invisible threads of causality that stitch reality together. So the next time you feel time slipping away, remember, you're not losing seconds. You're witnessing the universe's most primal language, the silent grammar of cause and effect, written in the bones of reality itself. What if the Big Bang wasn't the beginning of time, but the middle? Physicist Julian Barber's Janus point theory flips cosmic history on its head, proposing that our universe isn't flying apart from a single explosive origin. Instead, it's expanding outward in two directions at once, like an hourglass with time flowing both ways from a central pivot. Picture standing at the apex of a cosmic seesaw, where the past stretches behind you in one direction and the future stretches behind you in another. The universe, in this radical vision, is symmetrical, with two arrows of time branching from a single, timeless moment at its core. Barber's insight came from rewinding the tape of entropy. We know disorder increases as time moves forward, eggs break but never unbreak. But mathematically, the laws of physics work just as well if time runs backward. So why don't we remember the future? The answer might lie in the Janus point, named after the two-faced Roman god of transitions. At this critical juncture, entropy is at its lowest point, like the narrow waist of an hourglass, and the universe splits into two distinct temporal flows. One arrow points toward the familiar expansion we call the future, with galaxies drifting apart and coffee cooling in cups. The other arrow points toward what we'd consider the past, but for observers on that side, it's their future, with entropy increasing in the opposite direction. Imagine a crowd at a fireworks display, all facing inward toward the central explosion. Half see the fireworks bursting outward to their left, half see them bursting outward to their right. Neither group is wrong, they're just experiencing the same event from opposite temporal perspectives. In Barber's universe, before and after the Big Bang lose their meaning. There's no creation or destruction, just an eternal reconfiguration of matter and energy, unfolding symmetrically from the Janus point. The implications are staggering. If true, there could be another universe on the other side of the Big Bang, evolving forward in what we'd call reverse time. Stars there wouldn't fuse hydrogen into helium, they'd unfuse it, drawing energy from the cold void. Beings in that universe, if they exist, would remember events we consider future and perceive our past as their destiny. Causality would flip. A dropped glass on their side might shatter before it leaves the table, with the pieces seeming to leap together moments later. Critics argue the Janus point requires fine-tuning. Why would entropy be perfectly minimal at that exact moment? Barber counters that it's the only configuration where time's arrows can emerge naturally, like a ball balanced precisely at the top of a hill before rolling down. Others question how information could propagate coherently in two temporal directions, but recent simulations of simple particle systems show this dual-flow scenario isn't just mathematically possible, it's inevitable under certain conditions. The theory also dovetails with quantum weirdness. In quantum mechanics, particles don't always obey a strict past-to-future sequence. Some experiments hint that future measurements can retroactively influence particle states, as if quantum reality is stitching together causality from both temporal directions. Barber's model accommodates this seamlessly, treating time's flow as a local phenomenon rather than a cosmic constant. Perhaps the most haunting question is whether civilizations could exist on both sides of the Janus point. If so, communication would be impossible, not just because of distance, but because every signal they send would be entropy reversing noise to us and vice versa. Their progress would look like decay to our eyes, their technology uninventing itself as ours advances. Barber's vision doesn't just redefine time, it erases the very idea of a beginning or end. The Big Bang becomes less a birth and more a transformation, a cosmic pivot where time bifurcates like a river around a rock. So the next time you gaze at the night sky, consider this: half those stars might be flowing toward a future we'll never see, while the other half are echoes of a past that, from another perspective, hasn't happened yet. The universe isn't moving forward, it's unfolding in all directions at once, with the Janus point as its silent, timeless heart. What if entire centuries of recorded history were nothing more than an elaborate fabrication, a phantom timeline inserted by shadowy conspirators to rewrite humanity's past? This isn't the plot of a pulp novel, it's the spine-chilling claim at the heart of the phantom time hypothesis. German historian Herbert Illig stunned academics in the 1990s with his radical proposal: 300 years of medieval history, from the year 614 to 917, never actually happened. According to Illig, these lost centuries were invented by powerful figures, possibly Holy Roman Emperor Otto III and Pope Sylvester II, to place their reigns at the symbolic dawn of the new millennium, reshaping the past to serve their political ambitions. The theory hinges on peculiar gaps in the historical record. Illig pointed to suspiciously sparse archaeological evidence from this period, along with inconsistencies in dating methods like dendrochronology, the study of tree rings, which sometimes show mismatches with official timelines. Most damning, according to Illig, is the adoption of the Gregorian calendar in the 16th century. When Pope Gregory XIII corrected the Julian calendar's drift, the adjustment required skipping 10 days to realign with solar events. But Illig argued the math only works if you erase 3 extra centuries of accumulated error. It's like discovering your watch is set hours ahead, except instead of resetting it, someone inserted phantom days to cover the discrepancy. Could such a massive deception really be possible? Supporters highlight eerie parallels in art and architecture. The sudden appearance of Romanesque buildings in the 10th century, for example, lacks clear evolutionary precursors, as if styles leaped forward unnaturally. Even Charlemagne, the legendary emperor crowned in the year 800, has been questioned. Some scholars note his biography reads more like myth than history, filled with Christ-like miracles and superhuman feats. But mainstream historians dismiss the hypothesis as fringe fantasy. They argue Illig cherry-picks anomalies while ignoring overwhelming evidence like Byzantine and Islamic records from the Phantom period that align perfectly with Western accounts. Radiocarbon dating, though imperfect, consistently anchors artifacts to the disputed timeline, and the Gregorian calendar correction. Experts say Illig's math misinterprets the Julian system's actual drift rate, which accumulates closer to 1 day every 128 years, not the 3 days per 400 years he assumed. The most tantalizing question isn't whether the theory is true, it's why it resonates. Humanity's timeline has always been malleable. Rulers from Augustus to Stalin routinely altered calendars to cement power. The very concept of year zero wasn't standardized until the 6th century, when a monk named Dionysius Exiguus invented the Anno Domini system and likely miscalculated Jesus' birth by several years. History, it seems, is less a fixed record and more a palimpsest rewritten by each generation's biases. So while the phantom time hypothesis may crumble under scrutiny, its legacy lingers like a ghost in the archives. It forces us to ask how much of our past is fact and how much is the stories we've agreed to tell. Every date in a textbook, every royal lineage, every turning point, they're all threads in a tapestry that might contain more invention than we'd like to admit. The next time you glance at a calendar, consider this. Those numbers aren't just counting days. They're holding together a narrative that could, with the right pressure, unravel into something far stranger. We've all felt time play tricks on us, watching minutes crawl during a dull lecture or vanish in moments of joy. But what if these quirks of perception aren't just psychological glitches? What if they're hints that time itself is as malleable in our minds as it is in Einstein's relativity? Imagine an astronaut returning from near light-speed travel, aged only a few years while decades passed on Earth. Their body clock aligns with physics predictions, but what about their mind? Could consciousness itself warp time's flow, making relativity not just a cosmic rule but a deeply personal experience? Einstein showed that time slows near massive objects or at high velocities, a phenomenon called time dilation. GPS satellites orbiting Earth actually tick faster than clocks on the ground, their precision adjusted daily for relativity's effects. But here's the twist: human brains might mimic this cosmic flexibility. Neuroscientists like David Eagleman have demonstrated that during life-threatening events, the brain doesn't just feel like it's processing faster, it genuinely crams more perceptual frames into the same objective span. A car crash survivor might recall the wreck in surreal slow motion because their amygdala, flooded with adrenaline, hijacks the brain's timing mechanisms. It's as if extreme stress triggers a kind of biological time dilation, where consciousness stretches seconds like taffy. This blurs the line between physics and psychology. If a clock on a speeding spaceship runs slower and a traumatized brain perceives time slower, does that make subjective time just as real as relativistic time? Some theorists argue yes, that consciousness might be a kind of localized space-time curvature. In meditation studies, experienced practitioners can subjectively stretch minutes into what feels like hours, their brainwaves syncing in patterns resembling slowed temporal processing. Even mundane acts like zoning out during a highway drive, where you lose chunks of time, echo relativity's warping effects, as if attention and space-time are secretly entangled. The implications spiral outward. If time bends for both astronauts and adrenaline junkies, could our collective perception shape time's flow on larger scales? Philosopher Henry Bergson famously clashed with Einstein over this, insisting that lived time was fundamentally different from clock time. Bergson saw time not as a fourth dimension, but as a creative flux sculpted by memory and anticipation. Modern quantum theories flirt with similar ideas, like the delayed choice experiment, where a particle's past behavior changes based on future observations. It's as if reality waits for consciousness to collapse time into a coherent sequence. Then there's the eerie case of synesthesia patients who see time as spatial landscapes, months arranged in spirals or years as towering columns. For them, time isn't an abstract flow but a vivid, multidimensional structure. Could this be a neurological window into time's hidden geometry? Some physicists speculate that these perceptions aren't malfunctions but glimpses of a deeper truth, that time, like color, might be a spectrum we're only partially equipped to sense. Of course, skeptics counter that subjective time is just a clever illusion, the brain's storytelling trick to make sense of sensory input. But illusion or not, its effects are tangible. Placebo studies show that merely believing time has passed, like being told a painkiller takes 20 minutes to work, can alter physiological responses, as if the mind dials the body's internal clock forward. This raises a haunting possibility. If consciousness can locally override time's perceived speed, could there be entire cultures or eras where collective belief shaped temporal experience? Imagine a medieval monastery where monks, steeped in ritual, perceived days as longer than our hectic modern hours, not just poetically but physiologically. The mystery deepens when we consider dreams. In REM sleep, minutes of brain activity can generate dream sagas spanning lifetimes, a temporal compression that defies Newtonian logic. Some researchers propose dreaming as proof that the brain can simulate alternate time geometries, crafting fully realized worlds with their own rules of cause and effect. If so, is waking life just the dream where we've all agreed on the same clock? Whether time is ultimately a mental construct or a fundamental dimension, one thing's clear: the boundary between physics and perception is far thinner than we thought. Every time you check your watch, you might not just be measuring moments, you could be colluding with the universe to create them. So the next time an hour flies by or drags endlessly, ask yourself, are you tracking time or is time tracking you? Philosophers and physicists have been locked in a quiet battle over the nature of time, a clash between two visions so stark they've been dubbed the A theory and B theory. The A theory, rooted in human intuition, paints time as a flowing river, carrying us inexorably from the fixed past through the fleeting present into the open future. It's the view embedded in our language when we say things like "time marches on" or "that's all in the past now." But the B theory, inspired by Einstein's relativity, makes a radical claim: time doesn't flow at all. Instead, every moment, past, present, and future, exists equally, like frames in a film reel or coordinates on a map. The difference isn't just philosophical nitpicking, it reshapes how we understand reality itself. Einstein's equations treat time as a dimension akin to space, where now is as subjective as here. Just as two people might disagree about whether New York or London is to their left depending on where they're standing, observers moving at different speeds or in different gravitational fields experience time differently. A clock on a speeding rocket ticks slower than one on Earth, not because time is slowing down, but because the rocket's timeline is tilted relative to Earth's. In this framework, asking whether an event is really happening now is as meaningless as asking whether a star is really to the left of a galaxy. It all depends on your perspective. This challenges our deepest instincts. If the B theory is correct, your childhood isn't gone. It's just another set of coordinates in the space-time continuum, as real as the moment you're experiencing right now. Death becomes less an annihilation and more a matter of location, like a city you'll never visit again but still exists on the map. Even the Big Bang isn't a past event, it's simply the earliest point in the block universe's geometry. But does physics favor one theory over the other? relativity's math aligns neatly with the B-theory's timeless landscape, yet quantum mechanics introduces complications. At the quantum scale, particles seem to choose states when measured, as if the present moment holds special power. Some interpretations, like the Copenhagen school, even require a collapse of possibilities into reality, a process that smells suspiciously like a theory's flowing time. The debate spills into metaphysics. Theorists argue that without a genuine present, concepts like free will or moral responsibility crumble. If the future already exists, are our choices illusions? B-theorists counter that causality still holds. Your future self is simply the outcome of decisions you haven't made yet from your current vantage point. It's like reading a novel. The ending is fixed on the page, but the characters don't know it yet. Perhaps the most haunting implication is for consciousness. If time doesn't flow, why do we experience it that way? Some cognitive scientists suggest our brains construct the illusion of flow by stitching together sensory input like a reel of film. Others propose that consciousness itself is a process weaving through the block universe, creating the sensation of now as it goes. The truth might lie in synthesis. Just as light behaves as both particle and wave, time could be both static structure and dynamic flow, a duality where the A and B theories aren't rivals but complementary perspectives. After all, a map isn't the territory, and neither theory may capture time's full strangeness. One thing's certain: whether time flows or simply is, our place within it remains the ultimate mystery. Imagine dropping a pebble into a pond and watching the ripples spread outward, except in this case, the ripples also travel backward in time, influencing the moment before the pebble even left your hand. This isn't a scene from a sci-fi novel. It's the bizarre reality suggested by the time-symmetric universe, a theory where cause and effect aren't just a one-way street, but a looping highway where the future can reach back and tweak the past. At the heart of this idea lies retrocausality, a concept that flips our everyday logic on its head. The first clues emerged from quantum mechanics, where particles seem to defy classical rules. In the classic double-slit experiment, particles behave as waves when not observed, creating interference patterns on a screen. But the moment you try to measure which slit they pass through, they snap into definite particle states, as if they know they're being watched. This observer effect was strange enough, but then came the delayed choice quantum eraser, an experiment that cranked the weirdness to 11. In this setup, scientists could choose whether to measure a particle's path after it had already hit the detector. Astonishingly, the particle's behavior changed retroactively, as if the future measurement decision reached back in time to alter how the particle behaved in the past. It's like mailing a letter and then, days later, deciding whether to send it express or standard, only to find the postmark reflects that choice before you made it. How can this be? One explanation is that quantum events aren't fixed until they're observed, and that observation can happen in what we'd consider the future. In a time-symmetric universe, the distinction between past and future might be an illusion, a byproduct of our limited perception. Think of space-time as a vast, interconnected web where tugging one thread adjusts the entire pattern, regardless of when the tug happens. Critics argue retrocausality violates our intuitive sense of cause and effect. If the future influences the past, wouldn't that create paradoxes like a murder victim preventing their own death? But proponents counter that the universe might enforce consistency, weaving events into a seamless whole where apparent paradoxes cancel out. Imagine editing a movie scene after it's already been filmed. The final cut ensures everything fits, even if the editing decisions happened later. The implications are staggering. If retrocausality is real, free will takes on a new dimension. Our choices might not just shape the future, but also retroactively sculpt the past. Those eerie hunches or moments of déjà vu could be faint echoes of future events rippling backward. Even creativity might get a boost. Artists and inventors could be tapping into ideas their future selves haven't fully formed yet. The time-symmetric universe doesn't just challenge our understanding of physics, it redefines destiny itself. Cause and effect might not be an arrow but a dance, where every step influences both what comes next and what came before. So the next time you make a decision, consider this: the consequences might not just lie ahead. They could already be woven into the fabric of your past, waiting for you to catch up. There's a thought experiment so unsettling it makes the heat death of the universe seem cozy: the Boltzmann brain. Named after physicist Ludwig Boltzmann, this paradox suggests that in an endless sea of chaos, randomness could spontaneously assemble a fully conscious mind, complete with fabricated memories and a hallucinated reality. Picture waking up one day, convinced you've lived decades in a world of people and places, only to realize you're a lone, disembodied brain floating in the void, conjured by chance from the quantum froth. Your entire history, your sense of time, even this very moment, all illusions woven by particles colliding in just the right way to create the mirage of existence. This isn't just sci-fi speculation. Boltzmann's work on entropy showed that given enough time, even the most improbable events become inevitable. In a universe trillions upon trillions of years old, particles bouncing around at random will eventually arrange themselves into complex structures, including self-aware entities. The catch: it's vastly more likely for a single, isolated brain to pop into existence than an entire universe like ours. Statistically, you're probably that brain. The implications unravel time itself. If consciousness can emerge from chaos, how do we know any of our memories are real? That first kiss, your childhood home, the feeling of time passing. They could all be phantom imprints, generated moments ago in a cosmos otherwise devoid of meaning. The Boltzmann brain doesn't just threaten our sense of reality. It suggests time's arrow might be an artifact of faulty recollection. After all, if your brain formed 5 seconds ago with preloaded memories of a lifetime, wouldn't you swear time had flowed normally? Physicists have scrambled to resolve the paradox. Some argue that certain quantum conditions or cosmological constants make normal universes more probable than freak Boltzmann brains. Others propose that consciousness requires a rich, structured environment, meaning lone brains can't truly exist without a world to ground them. But the most haunting solution: the paradox might be unfalsifiable. If a Boltzmann brain's delusion is perfect, there's no experiment it could run to prove its own unreality. The Boltzmann brain forces us to confront time's fragility. If reality can flicker into being from nothing, then time isn't a river. It's a hall of mirrors where every reflection insists it's the original. Next time you recall a vivid memory, ask yourself, is this a thread in time's tapestry or just another glitch in the void's endless dice roll? Kurt Gödel, the same mathematician who shattered our understanding of logic with his incompleteness theorems, once handed Einstein a universe where time was nothing but a hall of mirrors, a cosmic labyrinth where the past, present, and future looped back on themselves like an Ouroboros eating its own tail. In 1949, as a birthday gift to his friend, Gödel presented a solution to Einstein's equations of general relativity that described a rotating universe, one where spacetime itself twisted into closed time-like curves. In this eerie cosmos, if you traveled far enough in any direction, you'd eventually return to your own past, like a record needle circling back to an earlier groove. Einstein was unsettled. His equations allowed it, but the implications were staggering. Causality could unravel. History might rewrite itself in real time. A traveler could witness their own birth, or worse, prevent it. Gödel's universe didn't just permit time travel, it demanded it as a feature of reality. The key was rotation. If the entire cosmos spun like a vast carousel, the drag of spacetime itself would warp time into knots. Picture a whirlpool where the water's motion pulls everything inward, except here, the whirlpool is reality, and the water is time itself, spiraling until it closes the loop. But here's the chilling part. Gödel's model didn't require wormholes, black holes, or exotic matter. The machinery for time travel was baked into the fabric of a spinning universe. Just pack enough supplies, set off in a straight line, and eventually you'd find yourself staring at your own back as you prepared to depart. No cosmic shortcuts needed, just patience and the grim realization that free will might be an illusion in a world where futures influence past. The philosophical fallout is even darker. If time loops exist, does the universe conspire to prevent paradoxes? Say you travel back to stop your parents from meeting. Would fate intervene, a slipped drink, a missed train to ensure history unfolds as it always did? Or does reality splinter into branches, each choice spawning a new timeline? Gödel himself leaned toward determinism, suggesting that in his universe every event was already locked in place like grooves on a record, your sense of making choices. Just the needle tracing a path that was always there. The real shocker, Gödel's universe might not even be fiction. While observations show our cosmos isn't uniformly rotating, some regions like the swirling accretion disks around black holes could mimic these conditions. Time might not loop globally, but locally, in pockets of extreme spin, the past could still be reachable. Even more provocative, quantum gravity models suggest space-time at microscopic scales might be foamy and chaotic, with fleeting Gödel-like loops bubbling in and out of existence. What does this mean for us? If Gödel was right, time isn't a river but a Möbius strip where every moment is both beginning and end. Your first breath and last sigh might be the same event, separated only by perspective. The next time you feel déjà vu, consider this. It might not be a glitch in your memory, but a flicker of the universe's true structure, a fleeting glimpse of time's secret loops waiting to pull you back in. What if time isn't built into the universe's foundation but painted onto its walls, like a mural that only comes alive when you step back? This is the spine-tingling revelation of the AD/CFT correspondence, a radical idea from string theory that binds time's flow to a hidden, timeless boundary. Imagine a prison where the inmates experience days and nights, unaware their entire reality is projected from patterns etched on the walls of their cell. That's the essence of this duality, a cosmic hologram where a universe with time, the bulk, emerges from a timeless, lower-dimensional surface, the boundary, like a 3D movie flickering from a 2D screen. The math behind this is as elegant as it is bizarre. In the late 1990s, physicist Juan Maldacena discovered that a particular type of universe, an anti-de Sitter space or ADS with negative curvature, could be perfectly described by a conformal field theory or CFT living on its boundary. The kicker, the CFT has no time dimension, yet it encodes all the temporal dynamics of the ADS space inside it. It's like writing the script for a play where the actors experience real drama while the script itself sits frozen on paper. How does this conjure time from timelessness? Think of a vinyl record. The grooves are static, but when the needle moves, music emerges, a sequence of notes creating rhythm. Similarly, the boundary CFT's quantum states play the bulk universe's time through their interactions. A single moment in the boundary might correspond to an entire history in the bulk, like a single frame of film containing the blueprint for a moving scene. This isn't just metaphor. Equations in the CFT precisely mirror events in the ADS space, with time emerging from the complexity of quantum entanglement on the boundary. Black holes turn this duality into a thriller. Normally, anything crossing a black hole's event horizon is lost forever, violating quantum mechanics' no deletion rule. But AD/CFT suggests the information isn't gone, it's smeared onto the horizon surface, scrambled like a cryptographic puzzle. From the boundary's perspective, time doesn't end at the singularity, it's just data being processed in a quantum computer. This could solve the infamous black hole information paradox, revealing that even space-time's most violent collapses are just shadows of deeper, timeless computations. The implications rewrite reality's rulebook. If time emerges from a boundary, then causality might be a secondary effect, like watching dominoes fall and calling it cause and effect, unaware someone lined them up moments before. Free will faces a crisis. Are choices genuine, or just the boundary's quantum dice rolling behind the scenes? Some theorists argue both are true, that the emergent time in the bulk feels real to its inhabitants, even if it's derivative. Experiments are impossibly distant. We can't craft ad-s universes in a lab, but subtle clues linger. Quantum error-correcting codes used in cutting-edge computing behave eerily like ad-s/CFT systems, with information distributed across networks in ways that mimic holography. Even more provocative, our universe on cosmic scales might approximate aspects of this duality, with the cosmic horizon playing the role of the boundary. If so, time itself could be a local phenomenon, a flickering projection in our corner of a vast, timeless multiverse. The ad-s/CFT correspondence doesn't just demote time, it redefines existence. What we perceive as history unfolding might be the universe's grand illusion, a performance staged by quantum actors who never experience the passage of moments. So the next time you check your watch, remember, those ticking seconds could be the universe's most dazzling magic trick, an act written in ink that never dries on a surface where now is just another word for forever. Quantum mechanics and general relativity are the twin pillars of modern physics, but when it comes to time, they speak entirely different languages. Einstein's relativity treats time as flexible, bending around massive objects like a rubber sheet. Clocks tick slower near black holes or speed away on rockets, proving time is just another dimension woven into spacetime's fabric. Yet quantum mechanics, ruling the subatomic world, acts like time is an unchanging stage where particles dance. It never warps or slows in Schrödinger's equation, just sits there, rigid and absolute, like a metronome counting beats in a void. This isn't just academic nitpicking. The clash between these visions leaves physics without a unified theory of reality, stranded at the edge of a paradox where time both bends and refuses to. Enter the problem of time, a puzzle so deep it's kept theorists awake for decades. In general relativity, the universe is a four-dimensional block where past, present, and future exist equally. But quantum mechanics insists events only become real when observed, as if time's flow emerges from measurement itself. Imagine two musicians, one playing a symphony where every note exists eternally on the sheet music, the other improvising jazz where the next chord doesn't exist until played. Reconciling these visions isn't just about equations, it's about deciding whether time is a fundamental truth or a cosmic illusion. Some solutions rewrite the rules entirely. Loop quantum gravity, for example, suggests spacetime isn't smooth but granular, built from tiny atoms of geometry that vibrate and connect like cosmic Lego. In this framework, time isn't continuous, it's a series of quantum jumps, like frames in a stop-motion film. Each jump tweaks the universe's structure, making time's flow an emergent property, not a backdrop. It's as if the ticking of clocks is just the universe refreshing its pixels. Then there's the radical path of timeless physics, the Wheeler-DeWitt equation, attempting to merge quantum mechanics with gravity, famously erases time altogether. Its math describes a frozen universe where change is an illusion, like a DVD paused on a single frame. Advocates argue time emerges from quantum entanglement, particles linking up in ways that create the appearance of sequence. Picture a crowd doing the wave at a stadium. No single person moves forward, yet the illusion of motion sweeps across the stands. String theory takes a different tack, proposing extra dimensions where time's behavior could vary. In some versions, time might be a shadow cast by deeper, hidden dynamics, like a puppeteer's hand unseen behind the stage. Or it could branch into multiple flows, each confined to separate branes of higher dimensional space. These ideas flirt with sci-fi, but the math hints that our linear time might be local, not universal. A being outside our brain could see time as a garden of forking paths, not a single river. The most provocative ideas come from quantum cosmology. The Hartle-Hawking no-boundary proposal imagines the Big Bang as a quantum event where time smooths into space like the rounded tip of a pickle. Here, asking what came before the Big Bang is like asking what's north of the North Pole, a question that loses meaning at the boundary. Time doesn't begin, it crystallizes from timeless quantum foam. Yet every solution raises new riddles. If time emerges from entanglement, why do we perceive it so vividly? If it's granular, what governs the rhythm of its ticks? The problem of time isn't just physics' greatest challenge. It's a mirror forcing us to ask whether time is out there in the cosmos or stitched into the fabric of our mind. One thing's certain, until we crack this puzzle, the universe's clockwork will remain half-hidden, its gears turning in shadows we've yet to illuminate. What if time isn't woven into the universe's blueprint, but computes into existence one quantum operation at a time? This is the radical proposition of emergent spacetime theory, where time and space aren't fundamental ingredients of reality but secondary effects, like the steam rising from a boiling pot. Imagine the cosmos as a vast quantum computer, where particles aren't just interacting, they're processing information in ways that spontaneously generate the illusion of time's flow. It's a vision that dissolves the familiar fabric of reality into something far stranger, a universe where time is code being executed, not a stage being occupied. The seeds of this idea were planted by quantum gravity researchers struggling to reconcile relativity's flexible spacetime with quantum mechanics' choppy discreteness. If gravity warps time like a rubber sheet, but quantum particles snap between states without smooth transitions, how do they coexist? The answer might lie in entanglement, the spooky link binding particles across distances. Recent breakthroughs suggest that spacetime itself could emerge from quantum entanglement, like a 3D hologram projected from a 2D surface. Every time particles entangle, they're not just sharing information, they're stitching together the very coordinates of reality. Picture a game of dominoes where each tile represents a quantum bit. Toppling one doesn't just knock over the next, it instantly influences tiles halfway across the board, as if space and time are irrelevant. Now scale this up to every particle in the universe, their entangled states forming a dynamic web. The dominoes don't just fall, they calculate, their collective interactions generating what we perceive as spacetime structure. In this view, the ticking of a clock isn't tracking some external time, it's displaying the universe's processing speed. Lab experiments are starting to catch up. In 2022, physicists used quantum processors to simulate microscopic models of emergent spacetime, observing how entanglement entropy, a measure of quantum connections, directly correlates with geometric properties like area and volume. It's as if the more quantum information particles share, the more space they create between them. Even stranger, when entanglement is disrupted, the simulated spacetime fractures, hinting that black holes, where spacetime seemingly breaks down, might just be regions where quantum computations crash. The implications rewrite cosmology's origin story. The Big Bang might not have been an explosion in pre-existing space and time, but the universe's very first boot up, when quantum information processing reached a critical threshold and spacetime crystallized from chaos. This could explain why time seems to flow in one direction. Quantum computations are inherently irreversible, like deleting a computer's temporary files. Each operation leaves a trace, creating the arrow of time we experience as entropy. But here's the twist: if spacetime is emergent, then now might be a local glitch, a temporary alignment of quantum calculations in your brain. Deep in intergalactic voids where entanglement is sparse, time could flicker like a bad Wi-Fi signal. Black holes might not destroy information but pause it, like a frozen quantum processor waiting to reboot. Even consciousness itself could be a side effect of the brain's dense entanglement network. generating the sensation of time's flow as it processes reality. Critics argue this reduces existence to mere computation, stripping time of its visceral reality. Yet supporters counter, isn't computation itself a kind of physics? After all, every quantum operation is a physical event, a particle spinning, a photon emitted. The difference is perspective. To us, time feels like a river. To the universe, it might just be the hum of a cosmic hard drive, endlessly rewriting its own operating system. So the next time you check your watch, consider this. Those seconds might not be passing, they're processing lines of quantum code, rendering the illusion of a universe in motion. Time isn't the director of this show, it's the special effect, blinking into existence one entangled calculation at a time. We take for granted that time is a straight path, one dimension where moments march from past to future. But what if time sprawls in directions we can't perceive, like a hidden labyrinth woven into the fabric of reality? The idea that time might have multiple dimensions isn't just science fiction. It's a serious proposal from physicists grappling with the universe's deepest puzzles. Imagine time not as a river but as a vast, branching delta where currents flow sideways, loop back, or even ripple into unseen depths. This notion springs from a simple but unsettling observation. Space has 3 dimensions, so why wouldn't time? After all, relativity already treats time as a dimension, one that bends and twists with gravity and motion. But some theories, like string theory, suggest time might have hidden dimensions coiled too tightly for us to notice. Picture a garden hose. From a distance, it looks like a one-dimensional line, but up close, you see its circular second dimension. Time could have similar hidden folds, where moments aren't just linear but stacked, braided, or layered. How would this manifest? One possibility is time's shadows, echoes of events that bleed across dimensions. Think of a flashlight shining through a prism, splitting into multiple beams. A major event, a supernova, a birth, might cast ripples into secondary time dimensions, creating faint duplicates or delays in how we experience it. These wouldn't be parallel universes, but parallel moments, like a single musical note resonating at slightly different times in adjacent rooms. Even stranger, causality could get tangled. In a world with 2 time dimensions, cause and effect might not be a straight line but a web. An event in time A could influence an event in time B, creating loops where the future affects the past in non-linear ways. Some models suggest this could explain quantum entanglement. Spooky connections. Particles might be linked through higher time dimensions, bypassing our linear notion of sequence entirely. But how would we test this? Some physicists propose looking for dimensional echoes in cosmic rays or particle collisions, anomalies where energy seems to vanish or reappear without cause, as if leaking into another time dimension. Others suggest that black holes, those natural space-time wrecking balls, might fray the edges of time's hidden layers, offering clues in their gravitational waves. The philosophical implications are dizzying. If time has multiple dimensions, free will becomes a kaleidoscope. Every choice might ripple across timelines we can't see. And death, just a transition from one temporal plane to another. The next time you feel déjà vu, consider this. It might not be a glitch in your memory, but a glimpse of time's true shape, a labyrinth where every moment exists in more directions than we could ever trace. Bill Murray waking up to "I Got You Babe" for the 1000th time in Groundhog Day captures something primal about time loops. The horror of reliving the same moments, the freedom of infinite do-overs. But while Hollywood paints time loops as quirky or terrifying, physics treats them as cold, calculable possibilities. Closed timelike curves, or CTC, aren't screenwriter fantasies. They're solutions to Einstein's equations where spacetime bends so severely that the future circles back to meet the past. The difference between fiction and reality. Pop culture loops are prisons for the protagonist. CTCs are cosmic roadmaps where every traveler is both prisoner and architect. Take Groundhog Day's rules. Phil Connors retains memories while the world resets, like a video game save point. But real CTCs don't allow selective recall, they demand consistency. In physicist Kip Thorne's wormhole model, if you travel back to sabotage your own birth, the universe conspires to stop you. A gun jams, a train delays, or maybe you just choose not to pull the trigger. This self-consistency principle turns paradoxes into closed circuits where cause and effect stitch themselves into an unbreakable tapestry. There's no cheating the loop, only fulfilling it. Films like Tenet flirt with this physics, showing bullets flying backward into guns as entropy reverses. But real CTCs don't require inverted time, just warped space. Picture a water slide so twisted it doubles back on itself. You're still moving forward, but the path itself loops. Gödel's rotating universe works the same way. Fly far enough in a spinning cosmos, and you'll return to your launch date without ever changing direction. No DeLoreans, no flux capacitors, just pure geometry. Yet fiction's emotional core reveals something deeper. When Russian doll's Nadia relives her death, each loop peels back layers of trauma. Physics can't explain why time would teach us lessons, but it does allow for quantum versions of growth. In some CTC models, particles interacting with their past selves create feedback loops that evolve toward stability, like a cosmic version of Nadia finally getting her life right. Maybe sentient beings in a CTC would feel that eerie déjà vu, their choices honed by millennia of invisible repetition. The darkest divergence, fiction's loops often enter. Phil escapes Punxsutawney, Nadia breaks her cycle. But CTCs are eternal. If you're in one, there's no exit, only the loop's unyielding symmetry. Every laugh, every heartbreak, every death must replay exactly forever. No wonder Einstein bristled at Gödel's math. It's a universe stripped of free will, where destiny is a locked groove in the cosmic record. So next time you watch a time loop movie, remember, the science is closer than you think. The fiction lies not in the loop itself, but in the hope that we could ever step outside it. What if the Big Bang wasn't an explosion in the void, but a cosmic metamorphosis, where time itself transformed into space like ice melting into water? This is the breathtaking premise of the no-boundary proposal, a theory crafted by Stephen Hawking and James Hartle that rewrites the origin of the universe not as a beginning, but as a smooth transition where the very concept of before loses all meaning. Picture a globe where asking what's north of the North Pole is nonsense. There's no edge, just a seamless curve. Hawking and Hartle's universe works the same way. At the Big Bang, time doesn't start, it bends into space, creating a four-dimensional cosmos with no boundary, no singularity, and no need for a creator's finger to hit the start button. The key lies in imaginary time, a mathematical trick where time behaves like space. In everyday life, we measure time in seconds, minutes, years. But in Hawking's equations, time can rotate into an imaginary dimension where it's no longer a straight line but a curve that closes on itself. Think of it like switching from Fahrenheit to Celsius. The temperature hasn't changed, but the numbers now follow different rules. At the Big Bang, real time, the kind we experience, emerges from this imaginary time like a sprout from a seed, with no sharp edge separating nothing from something. The universe doesn't appear, it changes like a river flowing seamlessly from underground. This solves one of cosmology's biggest headaches, the singularity. Classical physics breaks down at the Big Bang, where density and temperature soar to infinity. But in the no-boundary proposal, there's no singularity, just a smooth, finite geometry where space and time trade roles. It's like a painter blending two colors so perfectly you can't tell where one ends and the other begins. Quantum fluctuations in this primordial foam would naturally inflate into the galaxies and voids we see today, no divine spark required. But here's the twist: if time becomes space at the Big Bang, then asking what came before is as meaningless as asking what's outside the universe. The question assumes time exists independently, like a stage for cosmic events. But in this model, time is part of the universe's structure. It doesn't predate it. Imagine a novel where the first page doesn't say Chapter 1. It is the story with no preface or prologue. The universe isn't in time, time is in the universe. Critics argue the no-boundary proposal dodges the origin question by redefining terms. If time morphs into space, doesn't that just push the mystery elsewhere? Hawking countered that it's like asking what's south of the South Pole. The question dissolves when you understand Earth's geometry. Similarly, the universe might simply be, with no boundary conditions needing explanation. The theory also reshapes fate. Without a true beginning, the universe could be self-contained, needing no external cause. Quantum mechanics allows particles to pop into existence from nothing. Why not entire universes? In this view, the Big Bang isn't a one-time event but a natural phase transition, like steam condensing into water droplets. Some versions even suggest multiple bangs could arise from the same no-boundary state, like bubbles forming in a glass of soda. The most haunting implication: if time loops at the beginning, the universe might be its own parent, a cosmic Ouroboros where creation and destruction are two sides of the same coin. Next time you gaze at the night sky, consider this. Those stars might not be remnants of a beginning, but waypoints in an endless cycle where time and space dance eternally, neither one ever truly starting or stopping. What if our universe isn't the base reality, but an advanced simulation where time itself is just a variable someone can tweak with a keystroke? The simulation hypothesis, famously championed by philosopher Nick Bostrom, suggests that future civilizations with unfathomable computing power might create virtual universes indistinguishable from physical reality, and statistically, we're more likely to be inside one than not. But here's the twist: in a simulated reality, time wouldn't need to flow like a river. It could loop, stutter, or even run in patches, like a video game rendering only the parts of the world a player is actively observing. Bostrom's trilemma lays out the chilling math. Either almost all civilizations self-destruct before reaching post-human status, none choose to run ancestor simulations, or we're almost certainly living in one. The third option, as unnerving as it sounds, implies that time as we know it could be an optimized illusion. Think of a video game engine that doesn't simulate every blade of grass in real time. It only generates what the player sees. Similarly, our perception of time's continuity might be a clever rendering trick, with now just the latest frame being processed by some unfathomable cosmic GPU. This reshapes time's anomalies: déjà vu, a buffer reloading a previous save state; time dilation in relativity, the simulation allocating more processing power to complex gravitational fields. Even quantum superposition, where particles exist in multiple states until measured, could be the universe's lazy loading, avoiding unnecessary calculations until an observer forces a render. The double-slit experiment's baffling results start making sense if reality is running on hardware that prioritizes efficiency over fidelity. But could we ever prove it? Some physicists suggest looking for glitches, rounding errors in fundamental constants, or patterns in cosmic radiation that resemble compression artifacts. Others propose that a simulated universe might discretize time at the smallest scales, like a frame rate, leaving traces in high-energy particle collisions. There's even a wild idea that quantum entanglement's instant connections aren't magic, just two objects referencing the same memory address in the simulation's code. The darkest implication: if time is programmable, so is free will. Your choices might feel real, but they could be predetermined variables in an ancestor simulation replaying history for research or entertainment. The next time you linger over a decision, consider this. It might not be your deliberation the simulators are interested in, but the scripted outcome they've already debugged. What if every moment that ever was or will be is just as real as the chair you're sitting on, not memories or possibilities, but fixed points in an unchanging cosmic tapestry? This is the startling conclusion of the Retake-Putnam argument, a mathematical proof that drags eternity into the cold light of Einstein's relativity. Forget metaphors about rivers or arrows. This theory treats time like a frozen lake, where past, present, and future are simply coordinates on a map, all equally tangible. The argument starts with a simple observation from special relativity. Two events can appear simultaneous to one observer while happening at different times for another. Imagine a spaceship hurtling past Earth at near light speed. As it flashes by, the pilot might see a supernova explode in a distant galaxy at the exact moment they pass your hometown. But to you on Earth, that supernova happened years earlier or hasn't occurred yet. Relativity insists both perspectives are equally valid. There's no cosmic judge to declare who's really correct about now. Here's where it gets radical. If the present moment isn't universal, then your now is just a local quirk of your motion through space-time, no more special than your latitude or longitude. The supernova isn't future or past in any absolute sense. It's just elsewhere in the four-dimensional block universe. Dutch physicist Cornelis Retake and philosopher Hilary Putnam took this logic further in the 1960s. They showed that any event you'd call future must already be present for some observer moving relative to you. Chain enough of these perspectives together and every event, from Caesar's assassination to the heat death of the cosmos, must exist simultaneously in the grand mosaic of spacetime. Think of it like watching a movie on a DVD. The scenes aren't popping into existence as you watch, they're all already encoded on the disc. Your consciousness is just the laser reading one frame at a time, creating the illusion of flow. In the Retake-Putnam universe, becoming is a psychological trick. Being is the deeper reality. The implications rattle free will to its core. If the future is just as real as the past, does that mean your choices are illusions? Not necessarily. Some philosophers argue that your decisions still matter. They're just part of the eternal structure, like grooves in a record that produce music when played. Others see this as proof that time's passage is a cognitive artifact, a way for brains to make sense of a static reality. Skeptics counter that the argument conflates mathematical models with metaphysical truth. Just because relativity describes time as a dimension doesn't mean it is one ontologically. But supporters fire back. If relativity's predictions hold, and they do, down to GPS satellites needing corrections for time dilation, why privilege our subjective experience over the equations? The most haunting thought experiment comes from Putnam himself. Imagine a distant alien with technology advanced enough to see Earth in real time through a telescope. Due to light's finite speed, they'd always observe our past. But if they started moving toward us at relativistic velocities, their now would shift into what we'd consider our future. If they changed course, they could even witness events from our past and future simultaneously. This isn't time travel, it's the block universe revealing its true face, where when is as flexible as where. So next time you fret over a deadline or nostalgia for lost years, consider this: those moments aren't slipping away. They're locked in place, as permanent as mountains, just waiting for your consciousness to traverse them. The Retake-Putnam argument doesn't just reshape time. It turns existence into a grand gallery where every exhibit is eternally present, and the only thing moving is you. Most of us picture parallel universes as nearly identical to our own mirror worlds where you made different choices. History took alternate turns, or the laws of physics tweaked slightly. But Laura Mersini-Horton's timescape Multiverse shatters that cozy assumption, revealing a far stranger possibility that some pocket universes might not just have different histories, but entirely different directions of time. Imagine a cosmic froth where one bubble universe experiences time flowing forward like ours, while right next door, another bubble runs in reverse, with smoke pouring back into chimneys and broken teacups leaping onto tables to reassemble. This radical vision springs from the marriage of two ideas: eternal inflation and entropy. Eternal inflation suggests our universe is just one bubble in an endlessly expanding cosmic foam, with new universes constantly budding off, each with their own physical constants. Normally, we assume these sibling universes share basic features like time's arrow, but Mersini-Houghton, a theoretical physicist at the University of North Carolina, realized there's no law demanding this. Entropy, the universe's tendency toward disorder, dictates time's apparent flow in our world. Yet the starting conditions of each newborn bubble could lock in entirely different entropy gradients, meaning some universes might naturally run backward from our perspective. Picture a vast sheet of ice under a midday sun. As it melts, some puddles form where water flows downhill, while others, through random topography, might briefly trickle uphill before joining the broader current. Similarly, in the timescape multiverse, most universes might follow entropy's typical rise, but a rare few could flip the script. In those alien realms, heat would flow from cold to hot, information would unscramble into coherence, and beings, if they exist, would remember the future but anticipate the past. What's truly mind-bending is how these alternate time arrows might interact. Universes aren't completely isolated in Mersini-Houghton's model. They can subtly influence each other through quantum entanglement or gravitational echoes at their boundaries. Near the edge of a reverse time universe, our cosmos might experience eerie causality violations, particles that seem to respond to events before they occur, or shadows of objects that haven't yet been cast. Some theorists speculate that dark energy, that mysterious force accelerating our universe's expansion, could actually be gravitational leakage from a neighboring bubble where time runs backward, gently tugging our spacetime apart. The theory also reshapes the idea of cosmic beginnings. Our Big Bang might not have been an absolute start, but a local phase transition where a parent universe's timeline bifurcated, like a river splitting around a boulder, with one branch flowing left and the other right. In this view, the arrow of time isn't a fundamental law but an accident of birth, a quirk of how our particular bubble cooled from the primordial froth. Could we ever detect these mirror time universes? Mersini-Houghton suggests hunting for anomalous patterns in the cosmic microwave background, faint imprints left by neighboring bubbles in the multiverse's foam. Certain asymmetries or cold spots in the afterglow of the Big Bang might be bruises from collisions with universes where entropy runs opposite to ours. Others propose that advanced civilizations could engineer experiments to probe these boundaries, perhaps by creating micro-black holes whose evaporation emits telltale particles carrying signatures of reversed causality. The timescape multiverse doesn't just multiply realities, it redefines what reality even means. Time's flow, that most intimate feature of our existence, becomes a local custom, not a cosmic rule. The next time you watch steam rise from your coffee, consider this. Somewhere in the froth of creation, another version of that vapor might be doing the exact opposite, condensing into the cup, a silent reminder that even time's arrow is just one possibility in a much weirder tapestry. Why does time behave exactly as needed to allow stars to ignite, life to evolve, and minds to ponder its own existence? The universe runs on a startlingly precise temporal clockwork, one where even minor tweaks to time's fundamental properties would render complex structures impossible. This eerie precision is known as the temporal fine-tuning problem, and it forces us to confront a haunting possibility. The flow of time might not be arbitrary, but carefully calibrated for complexity to arise. Consider the cosmic choreography required for a single atom to form. After the Big Bang, the universe needed to expand rapidly enough to avoid collapsing back into a singularity, but not so fast that matter couldn't clump into galaxies. This balancing act hinged on time's relationship with gravity. If gravity had dominated too soon, stars would have formed prematurely and burned out before life could emerge. If expansion had won too decisively, matter would have scattered into eternal isolation. The margin for error was vanishingly thin, like a pencil balanced on its tip for billions of years. Even time's arrow seems suspiciously optimized. Entropy could have increased so rapidly that no structures more complex than scattered particles ever formed. Alternatively, it could have remained so low that the universe stagnated in a featureless soup. Instead, we inhabit a Goldilocks zone where disorder increases just fast enough to drive chemical reactions and evolutionary processes, but slowly enough for DNA, planets, and civilizations to coalesce. It's as if time's decay rate was fine-tuned to allow complexity to ride the edge between chaos and rigidity. Some physicists argue this precision points to deeper laws we've yet to uncover, a kind of temporal equivalent to the Higgs field that dictates time's behavior. Others propose more radical explanations. The anthropic principle suggests that time appears fine-tuned because we couldn't exist to observe it otherwise. In this view, our universe is one of countless variations, most of which collapsed instantly or froze into permanence. Only in rare realities like ours does time flow correctly for observers to emerge. But the most controversial interpretation whispers of design, not necessarily a divine clockmaker, but perhaps an underlying physics that naturally selects for temporal stability. Some versions of string theory predict higher dimensional geometries where time's flow self-adjusts to allow complexity, like a river carving its own banks. Others speculate that consciousness itself might play a role, that the observer effect in quantum mechanics extends to time's very structure, with intelligent life retroactively shaping the laws that allow its existence. The mystery deepens when we examine time's quantum granularity. At the Planck scale, time may not flow smoothly but progress in discrete ticks, like frames in a film. The interval between these frames is staggeringly brief, yet if it were even slightly longer, chemical bonds would fail to form, shorter, and quantum fluctuations would rip apart atomic nuclei. This precision isn't just convenient, it's existential. Whether through multiverses, undiscovered physics, or something stranger still, the temporal fine-tuning problem reveals time not as a backdrop, but as an active participant in creation. The next time you glance at a clock, remember, those ticking seconds might be more than a measurement. They could be the signature of a universe engineered by accident or intent to make moments like this one possible. What if time itself has an expiration date, not just the universe growing cold or collapsing, but the very fabric of temporal reality unraveling at its seams? Among the most unsettling possibilities is vacuum decay, a scenario where the universe's fundamental stability turns out to be a mirage. Picture space as a frozen lake, its surface seemingly solid. But beneath that thin layer of ice, there's a deeper, more stable state the cosmos could slip into at any moment. All it would take is a single quantum fluctuation in the right place, triggering a bubble of this true vacuum to form. This bubble would expand at the speed of light, rewriting the laws of physics as it goes. In its wake, time as we know it would cease to function. Atomic bonds might dissolve, forces like electromagnetism could vanish, and with them, any notion of cause and effect. There'd be no after, because the framework for sequences, memories, or even entropy would no longer exist. The chilling part, it could already be happening somewhere in the cosmos, and we wouldn't know until the wall of annihilation reached us, our last moment of time blinking out like a candle in a hurricane. Then there's the Big Crunch, a cosmic bookend to the Big Bang where gravity finally overcomes expansion, dragging all matter back into a singularity. But this isn't just a reverse explosion, it's time itself running backward from our perspective. Galaxies wouldn't just hurtle toward each other, the universe's arrow of time would invert. You'd see shattered cups reassemble, sunlight retreat into stars, and people growing younger until they vanish into their mother's wombs. Yet here's the paradox: for observers inside the collapsing universe, time would still feel like it's moving forward. It's the ultimate cosmic illusion, where the end looks like the beginning from the inside. Some theories even suggest the crunch could spawn a new Big Bang, not a rebirth, but a reset, where time's cycle begins anew with no memory of what came before. But the most abstract finale comes from Boltzmann's nightmare scenario, the Poincaré recurrence. Given enough time, quantum fluctuations in a dead, empty universe could, by sheer chance, recreate a moment indistinguishable from our present. Not a copy, not a simulation, but this exact now, recurring infinitely in the void. Your laughter, your regrets, the screen you're staring at, all resurrected by randomness over and over, in a cosmos where time has no meaning except as a countdown to the next accidental echo. It's immortality of the bleakest kind, not life after death, but the same life unbidden in a sea of meaningless eternity, the one thread tying these grim finales together. Time isn't just a feature of our universe, it's a fragile one, dependent on forces we barely understand. Whether it ends in fire, ice, or eerie repetition, the true lesson is this: every ticking second is a gift written on water, here until the universe decides to wipe the slate clean. There's a theory so radical it makes time itself a figment of your imagination, a shimmering illusion conjured into existence by the sheer act of observation. This is the wild frontier of idealist philosophy, where time doesn't flow like a river or stretch like a block. Instead, it flickers to life only when a conscious mind perceives change, like a projector beam illuminating individual frames of a film that otherwise wouldn't exist. Imagine a universe where the past isn't stored anywhere, the future isn't waiting, and now is the only moment that ever becomes real because you're here to witness it. The roots of this idea stretch back to thinkers like George Berkeley, the 18th century philosopher who argued that reality only exists as perception, no observer, no world. But quantum mechanics has given this ancient notion eerie new life. In experiments like the delayed choice quantum eraser, particles seem to decide their past behavior based on future observations, as if reality is assembling itself backward to match what conscious beings eventually see. It's like a detective solving a murder case, only to realize the victim's wounds appeared after he declared the cause of death. If particles can retroactively adjust to observers, might time itself be similarly flexible, a story we're narrating rather than a stage we're standing on? Some modern theorists take this even further. In Donald Hoffman's controversial interface theory of perception, time is a desktop icon on the interface of consciousness, a useful symbol that bears no resemblance to the deeper code of reality. Just as your computer screen hides the complexity of binary operations behind colorful buttons, your brain might hide the timeless chaos of raw existence behind the comforting fiction of seconds and minutes. Think of dreaming. In a vivid dream, you can experience days of adventure while your body sleeps for minutes. If time can warp so drastically in the mind, why assume it's fundamental to the universe? But here's where it gets dizzying. If consciousness creates time, then empty rooms where no one looks might exist in a weird quantum limbo, not just unobserved but unhappened. The moon isn't there when you don't stare at it. The dinosaurs didn't roar until the first paleontologist imagined them. This isn't just philosophy, physics is flirting with it too. The Wheeler-DeWitt equation, which describes quantum gravity, famously erases time entirely, suggesting our perception of flow might be a collective hallucination stitched together by entangled observers. Critics fire back. If time requires minds, how do we explain ancient geological processes or cosmic events predating life? Idealists counter that consciousness might not be human. It could be a fundamental property of the universe, with particles observing each other in a vast diffuse network. A rock doesn't ponder existence, but its atoms might participate in a primitive kind of perception, sustaining time's illusion at microscopic scales. The darkest implication: if time is a mental construct, death might not be an end, just the absence of a clock. Your final moment could stretch into eternity from your perspective, like a freeze frame you never escape, while the external world rushes on without you. Alternatively, if all moments are equally real only when observed, you might eternally relive your life's highlights in a fragmented mosaic, like a DVD skipping to its most played scenes. Whether time is a cosmic constant or a cognitive crutch, one thing's certain: the very act of questioning it proves that consciousness, at the very least, has the power to bend time's meaning. So the next time you glance at a clock, ask yourself, are you measuring time, or is time measuring you? From frozen block universes where your past and future exist eternally, to cosmic simulations where time is just rendered code, we've ventured through theories that don't just bend the rules of reality, they shatter them. Imagine a world where time loops back on itself like a Möbius strip, or where every choice spawns a new universe. Picture civilizations in mirrored dimensions aging backward, or the haunting possibility that you're a Boltzmann brain, conjured from chaos with false memories of a life that never was. These aren't just thought experiments, they're serious challenges to everything we assume about cause and effect, memory, and even free will. What makes these ideas so electrifying isn't just their strangeness, it's how they force us to confront the fragility of our everyday experience. That ticking clock on your wall, it might be a local quirk of a universe where time isn't fundamental, but an illusion stitched together by quantum entanglement. Your unshakable sense that the past is gone and the future's unwritten. In a holographic cosmos, those could be projections from a timeless boundary where every moment is already written, like a completed novel you're only reading one page at a time. So here's the real question. If time can be this fluid in the equations of physicists, how much of your life is truly anchored in reality? Those moments of déjà vu, the eerie sense that time speeds up or drags, could they be glitches in the matrix or glimpses of time's hidden layers? Maybe the answer doesn't lie in picking one theory, but in letting them all unsettle you. After all, the universe owes us no intuitive truths. If your head's spinning, good. That means you're paying attention. The cosmos is stranger than we'll ever fully grasp, and that's what makes it worth exploring. So keep questioning, keep wondering, and if you crave more deep dives into the mysteries of reality, hit subscribe. The next revelation might just rewrite your understanding of existence itself. Until then, remember, every second you experience is either infinitely precious or an elaborate illusion. Either way, it's a wild ride.